In the last lecture, we were looking at the impact of chlorofluorocarbons on depleting the ozone in the stratosphere. We saw there are hundreds of chemicals which were newly created by engineers which caused a depletion of the ozone layer. And some of them are given here, and they are used as reference chemicals, and any new chemical that is discovered or planned to be used is compared to these reference chlorofluorocarbons to decide how dangerous they are to the ozone layer. Here's an example, halon 1301. Okay? Its ozone depleting potential is 10 times larger than that of CFC11, which is a reference gas. So this means that we have to phase out halon 1301 faster than CFC11 because it has a greater impact on depleting ozone. So because of all these agreements under Montreal Protocol, the developed countries started reducing the production of ozone depleting substances, and their amount is measured in ozone depleting potential in tons of those substances. And you can see that from 1986, by the time we come to 1995, the European Community, Russia and US had reduced their production to a fairly low value, okay? Except for China, which was considered a developing country at that time. So it was allowed to increase its production, and it also started decreasing. So by 2008, almost all countries in the world stopped producing these ozone depleting substances. So this was a great success of the Montreal Protocol, that although when the protocol was signed in 1986, the science behind the depletion of the ozone was not fully understood. Okay? As the research results came out and various new discoveries were made, the protocol was continuously modified and made more stringent, so that by 1995, a drastic reduction of these ozone depleting gases had been made. Okay? So this is an important lesson that one learned from the Montreal Protocol, which was supposed to be applied to the Kyoto Protocol to control greenhouse gases. Okay? Now the impact of the Montreal Protocol on the amount of ozone in Antarctica was not dramatic. You can see that minimum ozone was depleting rapidly through the 80s when it was discovered. It continued to decline till 1995 because the production of the ozone depleting gases was not reduced rapidly. Okay? But after 1995, things remained fairly constant except for a minor increase in ozone. This variation you see after 1995 is partly natural variability of the climate of Antarctica. But by and large, you can see that from 1995 to 2006, the ozone minimum did not decline further. It was declining rapidly from 1980s to 1995 because of the release of all these substances which have a long lifetime. So even though Montreal Protocol was signed in 1986, one could not immediately reduce these substances. They took time. So the decline continued. So after 1995, the decline was not much. There was occasional increase in ozone amount. That is due to year-to-year variation in Antarctica, which is natural. Now here is an example of various chlorofluorocarbons which were rapidly reduced after 1990s, and most of them, especially CFC 113 is reduced almost zero. Others took a little more time because their amounts were very large. So by 2010, the emissions of these gases are almost reduced to zero. Okay. Now I want you to look at all these gases, okay, how they increased from 1960 to 1986 and then began to reduce. The emissions began to reduce, not the actual amount in the atmosphere. Started gradually, and you can see that by 2020 they had come to a level almost close to 1960, which shows the success of the Montreal Protocol. Here is another thing. This is a little more complicated. This is the burden. See, we may stop emitting these ozone depleting gases, but because they have a long lifetime, they remain in the atmosphere for a long period. So if you measure the actual amount of these gases vertical profile and integrate it, the burden in the atmosphere teragram was still quite high in 2000, okay, for CFC 12. Then slowly started declining. This is because of the long lifetime of these gases. So the damage that we have caused due to these gases will not go away before 2100. It will remain, okay. But we have prevented some serious damage which could have occurred. So this fact must be kept in mind when you talk about climate change, because climate change also involves carbon dioxide, which also has a long lifetime, 100 to 500, 600 years. So even if you stop releasing CO2 today, the amount of CO2 in the Earth's atmosphere will not go back to the value in 1850 very quickly. It will take a long time because of the long residence time of CO2 in the atmosphere. So this is a lesson we have learned from the Montreal Protocol that was there. Now one can look at positive effects. The fact that we were able to prevent the further depletion of ozone Antarctica, what did it do? It averted many deaths due to melanoma and other causes, okay. And so the estimate is that although right now the deaths averted is only around 1,000, but as the time goes along and the ozone depleting gases keep decreasing, you would have prevented more and more deaths, okay. So this is the positive consequence of Montreal Protocol, okay. And one more example showing the increase in these gases from the beginning of 20th century, first how it increased and reached a peak around 2000, although the protocol was signed in 86, but it still took time to start reducing, and then it started reducing, and our expectation is that it will continue to reduce till 2100. So these curves are important for you to understand climate change issues, because they are also carbon dioxide is not going to go to below 400 for quite some time. Even if you do all our attempts to reduce CO2 emissions, it will not immediately go down because it has a long residence time. So this fact must be kept in mind while you are looking at the data, okay. So the ozone depletion has been calculated, and so you can see that the change in amount of ozone amount kept declining up to year 2000, 2010. Now it will start increasing very slowly. So we will not reach levels of 1980 till about around 2040 or 2050. It will take time for the ozone to completely recover to a value which was there before 1980. Okay. So again, let's look at the ozone depleting potential. That is, how dangerous a particular gas is in depleting ozone compared to the reference of the chlorofluorocarbons. Okay. So the newer things introduced into the refrigeration and industries like the HCFCs, hydrochlorofluorocarbons, and HFCs, they are of course much lower ozone depleting potential than CFC, so are very good for preventing depletion of ozone. But some of these gases here, which are very good to prevent ozone depletion, turned out to have a large greenhouse effect. Okay. When this was discovered, the people who were involved in Montreal Protocol realized that they have solved one problem and created another problem. So they have been able to control ozone depletion, but they have introduced additional warming of the atmosphere by the very strong greenhouse effect of HFCs, which have a very long residence time. Okay. So if you compare carbon dioxide, which is our reference gas for climate change, with ozone, we can see that some of the gases which are being used now to prevent ozone depletion, their radiative forcing is not small. It's around 0.5 watts per meter squared. So that also has to be kept in mind. Okay, the role of these HFCs. Now I want to show you the satellite observed and model simulated temperature of the stratosphere. Okay, and you can see that the temperature in the stratosphere has been gradually decreasing over the last 20 years, okay, by about 1 degree centigrade. Okay. But in the middle, when there were volcanic eruptions in the 80s and in the 90s by Pinatubo, the suddenly temperature went up. This is because volcanoes release a lot of aerosols which go up to stratosphere, and some of these aerosols absorb sun's radiation and cause local heating, okay, of the stratosphere. So these two bumps are due to the release of aerosols which absorb solar radiation and cause warming for a short time. But when these aerosols are depleted, things go back to normal. But if you ignore these two bumps, you see a long-term trend of stratospheric cooling. Why is stratospheric cooling? Because stratospheric cooling occurs because of increase in carbon dioxide. So carbon dioxide is a greenhouse gas. It causes warming in the troposphere and cooling in the stratosphere. Now this comes as a big surprise to many people. They would like to know why CO2 behaves in one way in the stratosphere and in some other way in troposphere. Now to understand that, you must realize that the variation of temperature with height in the troposphere and stratosphere are exactly opposite. In the troposphere, temperature decreases as you go up. Once you reach tropopause, the temperature increases as you go up. Because of the difference in the lapse rate, the rate of change of temperature with height between stratosphere and troposphere, the greenhouse effect is exactly opposite. Now to understand, you must realize that because the temperature in the troposphere decreases the height, carbon dioxide which is there in the upper levels of the troposphere are at a colder region than the surface. So this carbon dioxide, which absorbs the radiation emitted by the surface, cannot emit this radiation to space with the same efficiency because the temperature of the upper troposphere is lower. That's why Earth becomes warmer, because the CO2 at the upper level cannot get rid of the heat as quickly as the surface of the Earth. But as you go up to stratosphere, temperature starts increasing again. So at the upper level of stratosphere, as CO2 goes up, it's able to more efficiently get rid of the heat. So carbon dioxide increase warms the troposphere but cools the stratosphere. Okay? But this warming you are seeing here in the mid 80s and early 90s due to volcanic eruption is totally different cause. It is due to the absorption of solar radiation by those aerosols in the stratosphere which are released by volcanoes. Okay? So as you can see, the stratosphere has a very complex feature. It is cooling slowly due to increase in CO2, but locally warming rapidly whenever there is a volcanic eruption. So this point I will further elaborate later today's lecture, because this has to be understood, otherwise there is a lot of confusion among people. Now this brings me to a point about how to understand the stratospheric chemistry and climate interaction. It's very important because chemistry plays a very important role in stratosphere because of the ozone layer. But there is also climate interaction between stratosphere, troposphere and the circulation. So let's look at the stratosphere. Aerosol contains ozone. Aerosol can affect the ozone, of course, and ozone can affect the temperature of the stratosphere. The greenhouse gases which are released by human actions, of course, cause the warming of the troposphere and cooling of the stratosphere. Okay? And there is also circulation in the stratosphere, although it's very weak, but it is there. It also has a role to play. And the other important factor is water vapor. As you know, as the temperature of the Earth increases due to increase in carbon dioxide, the water vapor in the troposphere is increasing. This follows thermodynamics, and this is a well-known Clausius-Clapeyron equation, which shows that as temperature goes up, the amount of water vapor in the troposphere will go up, and some of the water vapor reaches stratosphere, okay, and enhances the greenhouse effect. So you must remember that water vapor also plays a role, so do the ozone depleting substances. So stratosphere has a very complex structure. There is ozone being depleted by the ozone depleting substances, okay, and greenhouse gases are cooling the stratosphere. As the stratosphere cools, the stratosphere cooling, which is caused by greenhouse gases, as the stratosphere cools, there will be more clouds formed in the stratosphere. As you recall, some of the clouds contain ice, and this ice acts as a heterogeneous reaction site for the reaction between ozone depleting substances and ozone, okay, chlorofluorocarbons and ozone. So as the temperature goes down, the depletion of ozone increases. Okay. So here you see an interaction between greenhouse gases emitted by human actions and the depletion of ozone, okay, through the temperature decline. So the decline in temperature causes more depletion of ozone. So it is very important that we should cut down the greenhouse gas emission in order to maintain the ozone layer at a safe level in the upper stratosphere. So the point is that we have to understand the chemistry, we have to understand the radiation and the transport of water vapor into the stratosphere and other factors like dynamics which control the ozone amount in the stratosphere. So a lot of work is going on and new results might tell us something which we don't know. Okay. Now again let's focus on the lifetime of these chlorofluorocarbons, typically 45 years, 100 years, 85 years, 190 years, 1000 years. CCF 115 monochloro-pentafluoroethane is very, very dangerous because it has a 1000-year lifetime. So whatever I emit today will be there in the Earth's atmosphere for 1000 years. So it has to be completely banned because its global warming potential, that is its ability to cause global warming, is 7,370. Okay. So you have to keep in mind that among the various chlorofluorocarbons, some are not bad. Halon 1211 has only a lifetime of 16 years, but CFC 115 has a lifetime of 1000 years. So all these factors are taken into account in the definition of both ODP and GWP. For example, CFT 15, as far as ODP is concerned, that is ozone depleting potential, it is only half of CFC 11. So it's not bad for ozone depletion, but it's very bad for global warming. So there are a lot of conflicting issues in which we are trying to simultaneously reduce the potential of global warming and as well as depletion of ozone. So a number of complex factors come into play. That's why there are very complex negotiations under both Montreal Protocol and the Kyoto Protocol. Okay. So every substance we look at its ozone depleting potential as well as the global warming potential. Okay. Both are relevant and we want to keep both at a low value. Okay. And you can see that chlorofluorocarbon like CFC 11 are terrible from the point of view of GWP, is extremely large. Well, you look at methyl bromide, whose ozone potential is less than 1, it's good, and so is the GWP. Okay. So ideally one should be going for methyl bromide for various applications that we are thinking about, or hydrochlorofluorocarbons. Okay. Now people preferred hydrofluorocarbons, okay, which did not have chlorine in them, because they had almost zero ozone potential. But they discovered that some of them have very large global warming potential. So ultimately this also had to be banned because this is extremely high. Okay. So although it's good for preventing ozone depletion, it's very bad for climate change. And climate change ultimately will impact the stratosphere due to cooling of the stratosphere and will also ultimately affect ozone depletion. So this is a complexity that we have to deal with. Okay. So here is another list given by IPCC with various numbers which you can look at. And what I want to highlight is, from the point of view of both ozone depleting potential and global warming potential, we would like very short-lived gases like CH3BR3 because it has a very low ODP and very low global warming potential. But of course, for many applications it may not be suitable for other reasons. maybe cost, maybe availability and so on. So, but this table has to be continuously looked at in order to ensure that we don't release chemicals which have a high ODP or a high DWP. Both are bad for us for different reasons, okay, and one has to look at that. Now here is a table comparing on the right the GWP, on the left the ODP. So you can see that among them HFCs are bad because there were almost no ODP but a high GWP. Okay, so that's why recently this was completely banned. Its production was stopped because of the very high GWP it had. It was very fine for ODP, but unfortunately GWP was very large. So this kind of changes occur in the Montreal Protocol as new research and new results come out. So in October 2016, 8 years ago, the world's nations added the Kigali Amendment to the Montreal Protocol to control HFCs, because they found that the climate benefit of Montreal Protocol could be significantly offset by projected emissions of HFCs used to replace other ODPs, okay, ODP substances. So once this result came out, UN had to make a new amendment to the Montreal Protocol. So this will keep happening. As new research is done, new results are obtained, continuous modification of the Montreal Protocol will take place because of the fact that the research in this is still in infancy and new discoveries are made, and they call for changes in the protocol. Now the good news is that if you look at all the fluorocarbons we have been releasing, and if you weight it according to its ODP potential, these numbers kept going up till about 1989, and they have continuously come down. So this shows the success of Montreal Protocol, that we were able to successfully reduce the ozone depleting substances which cause the depletion of the ozone layer from a high value of around 1000 tons of these substances to almost zero by 2020. Okay? So this to me shows that countries of the world can work together and control the release of harmful gases through scientific research and agreements. Okay? So to me this is a positive sign that all countries in the world were able to get together and agree that these substances which were discovered and found were thought once to be very useful are not so useful now, and they were gradually over a period of 10 to 20 years brought down to zero. So this is the good news with which we must look at the Kyoto Protocol, which is there to control CO2, and so the success of the Montreal Protocol gives hope that similar agreements can be arrived at with Kyoto Protocol, although we have not yet succeeded. We have the Paris Agreement, which is not binding. We soon have to develop amendments to it to make sure that there are some binding constraints on the various CO2 and other gases which deplete the ozone layer, so which cause global warming. So that will take some time. So for example, the global production of HFCs, which was considered good for controlling what we call to keeping ozone layer undepleted. In 2002 it was around 500 million tons. It went up to 1000 million tons. Now we are going to put it to 0, okay, because you have discovered that it causes large amount of global warming. Okay. So the problem is that it is not going to, in spite of the Kigali Agreement, if we had not done the Kigali Agreement amendment, the HFCs would have continued to rise from emission of about 1 gigaton in 2020 to 6 gigaton. That will be stopped now because of the agreement. So it will start coming down, and you can see India was producing a lot of HFCs. Okay, so that will not occur now because of the agreement. So this is the success of the Kigali Agreement to restrict HFCs. Okay. So you can see that the various substances which was agreed to be controlled in various years here, and it took about 10 years to do that. This HCFC will take some more time, about 2030 when it's phased out. And some more names are there. The HCFCs which we discussed will be phased out by 2030. Okay? And so this kind of rolling agreements will continue to happen because of the new understanding of the chemistry of the stratospheric ozone layer. Okay? Now this happened because United Nations continuously provide assessments every few years from 85 onwards, various assessments about ozone layer, and based on this assessment the Montreal Protocol was modified continuously every few years. So this is the success of the United Nations Environmental Program. They provide a scientific assessment every few years based on which countries of the world agree to control the release of certain harmful gases. So this is the framework in which the Kyoto Protocol has to work on. So the lessons from the Montreal Protocol is the precautionary principle, that is, once you discover something bad is happening, you don't wait for the terrible thing to happen, you take advance action, precautionary principle to prevent it from happening. You integrate the new understanding in science with policy, recognize the needs of developing countries, give them time to control these substances. So it provides a way to international cooperation to solve environmental problems, and it differentiated between developing and developed countries. The developed countries were asked to take action first, and the developed countries were asked to follow later. Okay? And a lot of flexibility, because as we learn more and more about ozone layer and its complexity, we did more control. Okay. So that concludes the discussion on Montreal Protocol, and we will see how it impacts the IPCC and this one. I want to point out that it was quite easy to control CFCs because the industry involved in CFCs were only a few $1 billion. It is not going to be so easy to control the fossil fuel industry because it is worth a few $1 trillion. So this is a big challenge, although we will have learned a lot of lessons from Montreal Protocol, but the Kyoto Protocol will be much more difficult to implement because the industry that we are dealing with, that is coal, oil and gas, is much bigger. Okay? So with that I will conclude the discussion, but I want to point out a paper we have published recently which compares the difficulty in controlling the ozone layer compared to climate change, because climate change is a much more difficult problem. It involves many more industries and many more things that control our life. So it's not going to be that easy. I leave you with this table which you can look at comparing ozone depletion with climate change. They are very different in their construct, and so the number of countries involved in the negotiation in the original ozone developed with only 20 countries. But for climate change, all the 180 countries were involved because every country uses fossil fuels. And climate change has a neutral connotation because climate change can also occur naturally, and some countries may benefit from climate change, which is not true of the ozone hole. So there is some difficulty in convincing all countries that climate change is bad. Okay? So that took some time because countries like Russia thought that global warming will benefit those countries which are cold, but it is not true totally. Okay? And United States played a very positive role in controlling the ozone layer, but the same US Senate opposed the Kyoto Protocol. So that caused a lot of damage to the Kyoto Protocol. Okay? And right now the developed world is looking at the developing world as a competitor, which it did not do earlier. Earlier they thought that developing world were much weaker economically and they needed support, but now China has grown rapidly, so the view of the developed world is very different. So there are very complex issues involved in controlling climate change. So we will come to the issue later at the end of the course as to why we will have a lot of challenges in implementing the Paris Accord and make it binding. Okay? So Paris Accord, in contrast to the Kyoto Protocol, had no binding provisions, so it will take some time to come up with something which all the countries in the world can agree on. Thank you.